Okay, people. Okay, this is Alex Martelli. He needs no introduction. He will be talking about callback patterns and idioms in Python.
Thank you. Welcome, everybody. So this is in one of my design patterns talks. You can find several others on YouTube. I will not go a lot through what is a design pattern, why it matters, and so on, but just focus on the specific cloud of patterns that center around the concept of a callback with Python examples. This is the URL. It will be again on the last slide for the presentation. I will also keep trying to upload it to the PyCon site, but you know the connection of connectivity around here, so I apologize, but I'm even unable to completely load the page from which I should be starting my upload, much less actually complete the upload in any way. So, as usual, I try to explain roughly what level of skills I'm trying to address using the 3 levels of mastery. In this particular case, what I'm trying to express is that basically you need very little as long as you can follow just a modicum of Python constructs, like a bright beginner should pick up in a couple days. That way enough, I'm not going to require any particular knowledge, because I'm essentially presenting concepts and how they incarnate themselves in our code and our designs. So, callback. What's a callback? Essentially, it's any time that code that you reuse, don't supply, code that comes from a library, code that comes from a framework, calls back into your code. The back part of callback comes from the fact that for many decades in programming, the concept was that you called library. And when somebody first conceived this revolutionary idea that the library could call back to you, that needed to be distinguished from the normal case of you calling into the library. I believe that Richard Sweet of the Mesa development community first expressed this back in '85 as the Hollywood principle. The Hollywood principle is how a Hollywood talent scout kind of casts away somebody whose talent isn't enough for them by basically saying, well, thank you very much for all your information. Now don't call us, we'll call you. That meaning, don't bother me on the phone because you're not worth it. And this is actually not the spirit in which callbacks are used in programming. They're actually used for a lot of purposes, and I'm trying to put some order in the conceptualization of the many different ways in which they can be used. But summarizing to start, callbacks can be used and are often used for customization because they give you an enormous amount of flexibility. Also, callbacks are used for event-driven architectures in many apparently unrelated fields. And I try to analyze them into 2 subcategories, which is where actual events are concerned and you want to handle them, and when there's actually no event harmed in the making of this production, but we make up events as if they were events because event-driven is such a nice way to structure your code, and so we make up pseudo-events. I'll give copious examples, of course. You know, the key idea of design patterns is not something you make up, it's something you discover that people are actually designing this way and programming this way. And all my examples will be Python relevant. So the implementation in the most general term is very, very simple. You give somebody a callable, typically a function, but it could be a bound method or anything that can be called. Somebody may store it somewhere in a container as an attribute of some object, or maybe just hold it for a while as a local variable, as an argument, and calls it when appropriate. So what is the appropriate time for the callback to occur? Well, it depends on what the callback is being used for. If you're using it for customization purposes, then somebody calls the callback when it needs some functionality or information or configuration option to be specified. When you are thinking in terms of event-driven architecture, then the callback happens when appropriate events, relevant events occur. For example, a state change, a user action, a network event, and some other kind of I/O event, or a timeout, or a system event. And finally, the callback may occur when the appropriate event has been made up, as we'll see, for structuring of control flow in a very nice and decoupled way. So the simplest and most natural approach for callbacks is for customization. We're all extremely familiar with such a variety of callbacks for customization that it may actually become so familiar that we don't think of them as callback anymore, but they are, and that's very important. For example, consider the most common and the most useful example you can do in the Python standard library of callback for customization today. And that's customize how you sort a container. The introduction of the key equals parameter to sort and sorted by Raymond Hettinger was an enormous increase in the flexibility and the programming level of the Python sort without touching the underlying algorithm. It made it so much more flexible and useful because it basically subsumed what used to be known as a decorate, sort, undecorate, or DSU pattern. What passing a key equals something callback is doing is basically exactly the same thing as could be done in explicit Python like that. First of all, you build a decorated version of your list in this case, or other container, where the first field is what you obtain by calling the key callable. This is the callback point, the yellow one. And then just to make sure that items with equal keys are never compared directly, which could cause an error or some sort of misbehavior, we pass an incrementing index. And finally, the value itself just goes along for the ride. The incrementing index is basically to ensure that two things which happen to have equal result when subject to the key call just stay in the same order as they were at the beginning, so the sort is stable, which is an important, useful property. So once you've prepared this auxiliary list, you can sort them, and then you can basically extract the values back. You don't care about the keys, you don't care about the indices anymore in particular, just extract all the values and stick them back in the list. This is how we used to have to program until a few years ago when we wanted to do a flexible sort. There was another callback known as a comparator, but that's is very unusual for it to be the right way to do things in Python, because you end up with a number of calls to it that is way, way too high. And you also need to ensure, if you write a comparator, that it respects certain invariants which are not necessarily easy to ensure. While for the key, it's basically called exactly once for every item that you have to sort, which is the absolute obvious minimum number of times you may want to call it. And you don't have to ensure anything in particular except that it matches the semantics you're trying to get. For example, this is a case-insensitive sort of a list of keys. Basically, you're subjecting each keys to a pass-through to upper, and you're sorting on the uppercased strings with all the stability constraints and so on, and you're still having the original strings because we recover the original values, not the uppercase ones, with toss. But if you do it this way, you get much faster because it's all built into the Python internals, as well as being so much higher level, and therefore a closer way of thinking to what your problem is than to how the implementation solves it. One typical issue with callables is they don't necessarily the cleanest way of doing callables is not necessarily the best object-oriented way. So if what you want to call is actually a method which changes object by object, that's not immediately, it's not immediately doable in a callback fashion. In this case, we're bypassing the issue, and that's a pretty typical bypass, by kind of assuming that all the objects are going to be instances of string. And so we get the unbound method in this case, another popular way of writing a callback that actually goes and calls specific methods on the objects is with a lambda. Lambda x colon x dot some method, open close. That's another possibility. But it's also a workaround. The callback concepts, as you know if you're familiar with Mesa, comes from a more functional mindset than object-oriented mindset. It's still very useful in the object-oriented world, as we'll see, but it does require some messaging. When we want to do customization in an object-oriented mold, customization by callback in an object-oriented mold, the first thing we should think of is the template method design pattern. A template method design pattern has the callbacks happen inside a method of a base class and performs the callbacks by self-delegation. That is, it performs the callbacks on self. So the typical idea is the class template method parent has some method in which it calls self.SumHook, and your customization happens by subclassing the template method parent class and overriding the SumHook. This guarantees that the appropriate method gets called for each object because the object can define it itself. It's very handy, it's very compact. Sometimes it's a bit rigid, as is always the case with inheritance. Inheritance is rather strong, coupling is a rather rigid concept. So we can decouple, refactor, we reach towards other design patterns, classics of the object-oriented world, such as state and strategy. You should essentially check the presentations I've already given on template method, state, strategy. More generally, the behavioral patterns, the behavioral category of patterns has a lot of patterns that depend on an object-oriented version or variant of the concept of callback. Let's take another example, which is a bit purer, but is from the Python standard library, a case in which customization needs two functions, two callables. To schedule events, the sched module of the standard Python library, we actually need two functionalities. One which is some answer to the question, what time is it right now? And the other one which basically waits, sleeps, does nothing until the time has reached a certain level that you require. The object-oriented way, more structured, would be basically to pass to sched for customization purposes one object with two methods. So in this case, to run scheduler in real time as opposed to simulated time, we would just import the time module and pass it in the constructor of sched to obtain a scheduler that will call the dot time and dot sleep functions on the object we've passed. The functional programming way, which is more flexible but requires a little bit more care, is to basically simply pass the time.time and time.sleep separately. And if you're familiar with the Python standard library, you know that this is how the sched module of the Python standard library actually does it. You separately pass the .time and .sleep function. You have to be very careful, because if you pass two functions that are not actually coordinated with each other, you end up with a mess and your scheduling totally doesn't work. On the other hand, it is indeed much more flexible. Another option, a design option, whenever you have a callback to be used for customization is, are you providing a default value, or are you forcing the user to provide explicitly the callback functionality? For SCED, if I was designing it, I would probably say, well, hey, there is an obvious choice, which is just pass the real time and sleep functions, and isn't that what we'll most of the time want? But the designers of SCED in the standard library actually went the other way, probably to make the fact that there is a callback involved absolutely obvious to everybody. What they did was basically not give any defaults to those callbacks. So when you instantiate a scheduler, you have to explicitly tell the scheduler to use time.time and time.sleep if you want a scheduler for real time. So this is about what I have to say for callbacks for customization, and this might be a good time if there is any question specifically on the customization part of things before we move on to the more intricate world of event-driven architectures. So any questions? There will be plenty of time for questions at the end, but if you have some questions specifically on this part, I'm happy to take it now. No? Okay, let's move on. This was the simple part after all. So, events. By the way, who thinks they recognize why would this picture illustrate the concept of events? Sir? Exactly, they're bubble chamber event traces. Excellent. I was wondering if anybody would have the slightest idea of why I was showing this. It's very beautiful, and that's sufficient reason. So, the main point here is I want to distinguish event-driven architecture, which are based on things that actually happen or occur as events, and cases where the events are made up. There are pseudo-events that we're using for structuring our code, essentially. So what's our examples of actual events? Well, going back to the classic object-oriented design patterns, observable, is a classic design pattern which has actual events occurring, as in a state change to the object you're observing. That's the actual event. GUI frameworks are the most classic example in how essentially event-driven and callbacks entered the programming mainstreams, because there is a user out there who sometimes would like to forget about that and just go on with our beautiful programming, but alas, to pay the bills, you actually have to do something for the users. So the user is out there like mousing away and clicking keys and clicking keyboard keys and doing things. And as the user, independently from your computer, does actions, those are very naturally mapped into events that you must do something about. Maybe a little bit less obvious, but if you're connected to any I/O device, which should better be if your program is doing anything useful at all, such as a network, a disk, and so on, there are real-world physical events that happen, as in a bit has arrived on the network, the connection has failed, a certain time has elapsed without the connection succeeding, the record that I wanted to write to the disk has been written. That is, there is an actual thing out in the real world which we want to handle, that, okay, finally the data is recorded, so I can wipe it from memory, or, oh, finally the connection is open, so I can send hello world, whatever. And similarly, there are several system events callbacks, such as the system is starting, the system is going down, that kind of thing, that are actual events independent of our application code that we want to handle. Now, moving on to the pseudo events, I think the best example is so-called event-driven parsing. We'll get into details later, but it's pretty obvious that when you're parsing a file that you have there are no actual events involved. I mean, the file is there, you could parse it all, but that would essentially mean that you have to suck it all into memory, and that may take a lot of memory. So this clever approach basically parses it sequentially, and every time it recognizes something interesting, it generates a pseudo event that you can handle. Similarly, you can have scheduled callbacks. This is the flip side of SCED, which you've already discovered. Or you can have concurrent callbacks, threads, processes, and so on. And you can use callback-like concept to subject your code to timing measurements or debugging operations. We'll cover each of these points later. But let's go back to the observer design pattern. So the observer design pattern has the concept of a target object that can be observed. So basically it's an observable object. And you can add observers to it, and that could be simple callables in a multi-paradigm language like Python, or they could be objects with suitable methods. When the target state changes, the target object knows that it needs to inform of this event all the observers, so the observers can do whatever it is they do. It's like totally decoupled. There has no need to know why somebody's interested in the state changing. You still have several design choices to make when you implement observer. One is, are you going to use general or specific observers? A general observer would basically be whatever, for any state change, call me back. I don't care what kind of state change, just call me back as soon as feasible after the state has changed. This might be, for example, needed, or the best way to do things, if what you want to do upon state changes is save the object to disk. Make sure the disk image of the object reflects whatever the live object in memory is up to on a continuing basis. Then in this case, anytime the state of the live object in memory changes, you need to be alerted because you need to save the change. Specific changes are when this attribute changes, or you can have more and more filtering on it. So I don't care to be alerted until the temperature attribute goes above the value 75. And this would be a very specific case. So, of course, you can solve exactly the same problems in both cases, but the amount of coupling and code you need for one and the other is quite different. Also, you may choose to have specific observers. This is kind of similar to what we already remarked on for the customization side of things. For SCED, you could have one callback for this kind of change, and a different callback for this other kind of change, a different callback for this other kind of change, or you can group them, for example, into an object, which must have appropriate methods to be called for the different kind of changes you're going to deal with. So the GUI frameworks, which can be seen as the motivation, the main motivation for originally having callbacks and the main motivation for originally abstracting the observer pattern, basically they are the most classic of event-driven fields. Just about every GUI framework these days will have observer patterns, that is callbacks for you to use. So I'm giving tkinter as the Python example because it's the closest thing we have to a standard GUI for Python. You have two groups of callbacks in tkinter. One is very elementary callbacks and the other one is very advanced stuff. The elementary callback is typically the command equals parameter that you pass when you construct a button. The only event that is watching for is a click. So there's nothing much connected to it except, oh yeah, finally the user has clicked this button. So you pass an observable which gets called whenever the user clicks that button. And that's like the most elementary kind of callback you can imagine. At the other extreme, there is the bind verb and a few related ones such as bind all and so on, if you're familiar with tkinter, where you basically can describe an event of interest. In this case, if we call bind on a specific widget, it's going to be events on that widget particularly, but with bind all, it would be events anywhere in the user interface and so on. And the string with which you describe the event can be extremely detailed. For example, quote less than key greater than means any keystroke. But if you are only interested in the user clicking on A, you could have the event description string quote A quote. So, and of course there are many mixes you can have. So you can answer to any key or to a specific key or to the mouse pointer entering a widget or leaving a widget. So at there is basically this little interpreted languages embedded that takes that string and understands what kind of events you are actually trying to handle. And that, of course, is you cannot inform all constraints. For example, you might want to be called only when the mouse leaves from the left side of the object. You don't care if it leaves from above, below, or to the right, but if it leaves to the left, you need to do something. I can't imagine exactly the circumstances, but you know, it's hard to imagine user interfaces in general. So how would you do that? Well, you'd have to get your callback on every leave event, and then the handler that you pass gets an event object as an attribute, and it can check, for example, the coordinates of the mouse, .x and .y, on that event object to see if the mouse has gone out from the left or elsewhere. So you can do some selection in the description string, and the rest you will do in your code. So let's take a step back and thinking of observer and GUIs reflect on what design issues are always going to be present in this kind of callbacks. Well, one of the main ones is, okay, so what arguments? Oh, you're going to call me back. Great. With what arguments are you going to call me back? The simplest, it's like that command thing, is no arguments. It's just something happened, whatever it is. So you have to be very specific in your binding because you are going to get no other information besides something happened because you get called without any argument. So it's simplest, but it's very hardly ever what you actually want. In the observer, a good solution would typically be to pass the target, what is it you're observing, as the argument of the callback. So you can have one observer observing many observables. Sorry for the pastiche here, but the terminology is that way. You can look at many targets from a single callable without having to have state separating the callbacks, because what is the observable that has changed state, you'll be told by being passed to the target object when you are called back. Or you could have a description of the state changes. If you are told that the object that changed, you can basically get attributes from it or call methods on it to find out exactly what changed this time. But this can be a bit slow, particularly if you're not talking about objects sharing memory in the same process, but there's some round trip involved. And it's also a lot of code that you may have to write. So sometimes it could be handy to have as an argument a compact description of what exactly has changed in the state of the object you're observing. Or you could have, if for more general event-driven, some description of the event or identifier of the event, or again, something more specific. This is an important design choice whenever you design this kind of system. But also, you may want to have arguments that are not actually related to the target or the event that just happened, but that essentially customize the callable itself, because you may have a callable which is going to be called with one argument, but it actually takes two, and you want to specify one at setting time to customize behavior. So when you want to have, in general, fixed arguments in callbacks, the general purpose Python solution is the functools module of the standard library. Functools.partial lets you take a callable and pass a certain number of fixed or named argument to it to pre-bind. So those will be used in all of your callbacks. However, many, well, not all, but quite a few of the Python occurrences of callbacks let you use, instead of this kind of syntax, where basically you are using functional partials, a perfectly general system to do the pre-binding, they let you use this approach instead, where you set the callback, you pass the callable, and optionally any predetermined argument that you want to pre-bind on the object. And this is so much nicer to write. This is more general, but this is definitely nicer. So consider your audience and how often will they want to pre-bind arguments when you design a callback system. Another issue is, how do you dispatch callbacks? If more than one observer is interested in a certain object, or if more than one callable gets set as the handler of a certain event, what do you do then? Do you remember just the latest one set. That's very simple, and it's typically what would happen, for example, in a system such as TK interbind. Why is it so nice? Well, because it's obviously easiest to implement. The observable basically has to have one attribute, which is who shall I call one. I will call one callables, and it's very easy to replace things because basically whatever you're setting takes place of what used to be there. Or in many cases, you actually want to call them all, but then you have to make some design decisions. In what order are you going to call them? Last in, first out, random, no guarantees. Then you could just keep a set. How do you remove a callback? That's not really a problem if you have only one callback set, because you can always put, say, none there to mean, okay, no callbacks are needed at this time if this event occurs. If you do have support multiple callbacks being called in a certain order, then you also need to provide a separate way to remove a callback, otherwise your system gets very, very inflexible. And finally, if you do have a specified order, a crucial design decision is whether one of the callbacks can decide, okay, I have completely handled this event. Nobody that would normally be called after me is going to be called I'm preempting. Whether that is allowed or not makes a huge difference to your event system. And finally, the design decision, which I already mentioned a couple of times, is whether it makes sense to group things, such, for example, in using objects with methods that get called appropriately. Another issue is whether errors need to be distinguished from other kind of events. Errors might normally be, for example, Python exceptions if you're dealing with Python code, but consider an I/O system. An error is something defined by the I/O hardware, such as a connection failed, such as the disk is broken, so I can't save your data, and so on. Should they be treated as normal events or singled out somehow? The best design for all of these issues that I've ever found can be found at that URL, and is the deferred pattern originated in the Twisted project. Essentially, one deferred object structures callbacks. There's a chain of callbacks to be used for the normal case and one to be used for the error case, and a very clean, very simple protocol in which they're handled. So basically, each callback is held with its arguments, positional and named, and one more argument identifies the event or the error, and it can be chained because basically the result of any callback is passed as the one argument of the next callback. So you have a lot of clean, structured flexibility. And the last but not least, a very important example of actual events are system events. For example, one of the most useful one, if you need to do any cleanup just before the program terminates, you can pass your callable to the register function of the attexit module of the standard library. This guarantees it gets called back in some order, no guarantee of order, and you cannot preempt in this case, when the whole program is just about to shut down. That can be very helpful. You can close things, clean things, delete temporary files, but all the sort, and it will be called whether Python is terminating normally or by exception propagation. It will not be called if the Python C-coded binary crashes, because then there is a bug in Python itself. But that, in this case, you need other design architecture patterns that I'm not covering in this talk, such as the watchdog pattern. Another example, which is not so much Python specific, is the signal concept, whereby it's originally a Unix concept, but there's some traces of that in Windows too. Some external events, typically the user calling kill or so on, can send a signal to your program. There isn't all that much information connected with the signal, but you can still handle it. Python also offers several hooks and a trace hook. Unfortunately, the syntax is slightly different. If you want to set the callable that gets called back whenever there is something to, for example, display in an interactive session, what you do is sys.displayHook equals callable, while if what you want to do is for it to be called on every line that gets executed, then you call sys.setTrace with your callable. It's basically the same concept, except that this happens for every line executed in a script, and is how all sort of debugging and tracing and so on can be implemented easily in Python. Extension modules have their own system events. For example, the readline module can do certain callbacks so that you can specify when it's starting up, just before it asks for input, and when the user asks for completion, for example, by pressing the tab key after entering a few characters, you can write the completer callback, and it needs to respect a certain protocol, of course, and it will be called back as you require. And then finally, we move to the concept of pseudo events, which are basically motivated by the fact that events are a nice way to structure control flow, or can be. So we can make them up. And these are a few examples. Let's start with the parsing concept, for example. One system that really made the idea very popular, originally for Java, but soon ported to Python as well, was Sax, the simple parser for XML. Instead of basically sucking all the XML document, which could be very big and of which you might be interested only in a few details, into memory, which can be very, very time-consuming, it treats each start of tag and end of tag as a parsing event and calls you back appropriately. So your handler needs to keep structure. For example, if you're only interested in the foo tag when it's embedded in a bar tag, then you can keep very simply a small stack of what tags are open now. So when the foo is open event gets called, you can check in the current stack whether there's a bar event open. There's also a not really event-driven system known as the pull DOM, which is a very interesting concept, which basically switches from callbacks to stream, which is a common duality that I'd really like to explore but can't fit in the space of this talk. But basically it lets you expand only certain subtrees as you need. We've already mentioned SCED, but the point of SCED is having scheduled callbacks. So basically you enter or interrupts callbacks to be done with a certain delay and a certain priority. You can cancel callback, and eventually when you have set up the initial set of callbacks that describe the set of events, you call s.run, and that basically just does all of your callbacks. And that may not necessarily terminate because a callback may re-enter itself, so it can be done every 200 milliseconds. The way you get that is by having s.enter as the first instruction in the callback. And concurrent callbacks are ones that happen on a separate thread or process, or even a separate node. The most popular, of course, is threading, but which basically has as its artificial event the fact that you finally called the t.start. That's not much of an event because it's something you're doing in your own code, but the point is that it does your callback in a separate thread, so that subject to certain constraints such as GIL if you're using CPython, but hey, there are other implementations, things can happen simultaneously. The stackless, sorry, this is actually stackless, not stacklet, I apologize. The stackless module does that without actually involving the CPU threading, and basically you set up callbacks and it does a round robin call of all of your callables with the concept of channels and reactivation and rescheduling, of course. There's a processing third-party module which tries very hard and almost succeeds in doing exactly what threading does, except in multiple processes, so you don't have to worry about GILs or things, or even running on several different CPUs within the same module. And then there are more advanced distributed computing environments such as network spaces, NWS, whose SLAY component basically can do callbacks on separate nodes. For example, if you have a collection stored in a network space, you want to do something to each element, you can call slay.eachElem, and it will do your callback on separate nodes. It basically sends your bytecode across to the nodes and executes it and so on. Last but not least, timing and debugging often use callback approaches. In this case, there's a little variant which basically exploits the fact that Python is a dynamic language. Instead of actually passing a callable, you can pass a string, which basically is telling the framework to compile that expression or statement, depending on the case, before it actually goes and executes it. As you can see, the events are actually very artificial, because setup is basically before you do the timing, and the statement event is basically whenever you feel like it, you call it until you have collected enough data to be able to say something about its timing. Similarly, for debugging, PDB lets you use strings. So you can use run or run eval if what you want to do is pass it a string and have it compile it, or if you already have the callable, which is the normal callback case, then you use run call. And again, here the event is immediate, but with, so if you do a pdb.runCall my function, what happens is that my functions immediately starts executing with the specified arguments, but then before its very first statement is executed, you get a debug prompt, and you can give debug commands. So, and then you can single step, and so on and so forth. So basically, you can see why I want to consider this approach to callback as separate from the one in which actual events occur, because here it's pretty obvious, and more obvious, I hope, as I went through the various kind of examples, that the events are totally made up and are simply nice ways of structuring the execution of our code. And this leaves us 5 minutes for question and answers. Actually, since we are due for the break, if we take a little bit more than 5 minutes, just anybody who's not interested can simply walk, and the rest of us can, I think, take a few more minutes. So, questions? Have I been so exhaustive or so boring? Please. So, do I have any strategies for handling errors in the context of multiple callbacks? I believe that twisted deferred is the best designed structure to organize that. It's basically a deferred has two, you can consider them linked list of callables. One for the normal case, and if an error happens either before or even during the processing, then you switch over to the chain of error handlers. Basically, the exception object gets encapsulated and passed into the error handlers, and you can have many steps there. That's a very simple structured concept, and it's really incredibly flexible. You might not think, well, it's only like a single linked list, but it does all you need when you use it properly. That's why even if you're not using twisted, because the events you're handling are completely different, you should consider using specifically the deferred to organize your callbacks. It's really very handy. So for simple cases of callbacks, how do I compare generators and other iterators to the callback slash event concept? And the questioner asked, for example, for stacks versus elementary. So this is a dualism between the callback and the stream concept, which I wish I had time to explore in this talk. Unfortunately, I didn't. But so in a sense, at least in some cases, the callback is, okay, here is my code, give it into the framework, call it for every object that happens or gets generated and so on. And that's very much the small talk slash Ruby concept of iteration. It's all based on certain code that gets injected and gets called back appropriately. In Python, we tend very often to flip that like a glove and get the generated objects out so we can process them in line rather than injecting the code. And the actual power of the two concepts is just about equivalent, but they come in handy and are most elegant for different kind of work. If you actually have objects that are considered one after the other, the explicited out loop that Python prefers ends up being much more elegant than the injection of code. But there are other patterns, for example, with a Ruby iterator or Smalltalk iterator, you can implement essentially any control structure, such as an if. Basically, the callback will never happen unless and until some condition gets satisfied, and that doesn't require everything else to block. While if you do it with a for loop, if nothing comes out, then what you do? Wait forever? You block there. That's not at all as elegant. Yeah, you can hack it by basically having a generator whose next is going to be called if appropriate, but it's definitely not as elegant in this case. So there is another entire presentation here discussing the duality and the advantages of the two approaches. You can use both, but as a simple example, which I mentioned very much in passing, that's what pull-down does. It basically gives you the events instead of by calling back as a stream. So that is basically how you pick which ones you want to iterate. And that's reasonably appropriate because it is indeed a stream. Things do happen, like this tag opens, this tag opens, this tag close, this tag close. So it's quite appropriate for that. But then, of course, you do have the switching back to the DOM approach where you expand the subtree because otherwise you couldn't do much with it. So it's not as pure as the pure event-driven, if you see what I mean. It's very practical, but we know that in Python, practicality tends to beat purity. One more official questions, I think, and then we can have more, but maybe not so formally or not recorded. Anybody with one more? Yes. So there is a reason design patterns are design pattern. Oh, sorry. The question is, so can this design pattern, I actually presented several in the course of this talk, although I didn't name them, so it's my fault. Didn't name all that properly. Be encapsulated in one simple piece of code. Some of them can and some of them can't, and that's why they are design patterns, because they are more in your mind before they get into your code. You think of, should I have a callback here? How you encapsulate that? Well, it's pretty easy. You have a callable as an argument to a method that does self dot the callable equal whatever I was passed, and then later calls it. That's pretty trivial, but the point is, when is that a good idea? So for example, let's focus on configuration issues. Suppose that every time the thing, a window repaints itself, it calls, so it needs to know what color. Well, why not just give it a attribute color statically, and basically whenever it needs to repaint itself, it uses self.color. Well, that's very nice, but it's not quite as flexible, because if every time it paints it called the callback giving it the color, you could implement special effects whereby the color changes and shimmers and does things. It will be very computationally intensive compared to just looking at a fixed number, but much more flexible. So a call always has a cost. A microsecond, a fraction of a microsecond. If you do it 1,000,000 times, that's seconds. But that cost may be worth paying if things become much more flexible and you are interested in making use of that flexibility. Now, this is not necessarily the case. For example, I can't imagine a key function for sorting that picks the key semi-randomly, so things sort of kind of confusedly. But hey, you could do that. You could add a random noise while you're extracting the key. Why not? I don't see why you want, but maybe for some visual effects that would be nice. I don't know. So this is more about why would I want to do that? What are the forces that I'm trying to solve by having a callback, rather than how do I do it? Because how is very easy. You pass a callable, you call the callable, and that's all there is to it. But why are you passing it, and why are you calling it? That's an interesting part. What are the forces you're solving? What is the motivation for doing this in the first place? Okay, I think this is just about the right time to finish.